Hello again. Today we're continuing our discussion on acids and bases. So today we're going to start by discussing the autoionization of water. Last time we saw that water is amphoteric, which means that it can act as either an acid or a base. Now that means that water can react with itself. So when water reacts with itself, this is called autoionization. So you'll notice down below we have two water molecules. And let's label one the acid. So I'm actually going to erase that line there. And we'll label the other water molecule the base. You'll notice that at the end of the reaction, we end up forming the hydronium ion, which is the conjugate acid, and the hydroxide ion, which is the conjugate base. Let's actually draw out the arrow pushing mechanism for this reaction. So in the space below, I'm going to draw the Lewis structures for both water molecules. And let's draw those arrows. So if the water molecule on the right is the base, that means that it's going to accept a hydrogen from the acid. And then as before, we showed that the covalent bond electrons are going to remain on the acid. So at the end of that reaction, we have again the hydronium ion and the hydroxide ion. Now the other way that we could write this reaction, we could just show that water is going to ionize. So we could show that water is splitting up into a hydrogen ion and a hydroxide ion. Now you'll notice we are using double arrows here, so this is a reversible reaction. And in particular, this reaction does favor the reactants. So we don't produce very many hydronium ions or hydroxide ions. So actually down below, I'm going to draw a double arrow just to be consistent there. Now, what's really interesting is that in aqueous solutions, because water is present, there's always going to be some amount of both hydronium ions and hydroxide ions. Now, because water is reacting with itself, we should end up with the same amount of hydronium ions and hydroxide ions in water. So the concentration shown in brackets here for the hydronium ion is going to equal the concentration of the hydroxide ion, and both of their concentrations will be equal to 1.0 times 10 to the negative 7th moles per liter at 25 degrees Celsius. Now, one thing we can do is multiply those concentrations together. So the product of the concentrations of those ions is called the ion product of water, or another name for it is the dissociation constant. And the symbol for this constant is Kw. So if we do multiply those two concentrations together, we'll end up with a value of 1 times 10 to the negative 14th, at 25 degrees Celsius. Now, what's great about this ion product constant is we can use this in other situations where maybe the concentration of hydronium ions is not equal to the concentration of the hydroxide ions. So this constant is true for every solution. So even if hydronium ions are present to a greater extent in solution, that just means that the presence of the hydroxide ions will be smaller. So another way of saying that is as the concentration of hydronium ions increases, the concentration of hydroxide ions must decrease so that the product constant stays the same. So the concentration of the hydronium ions is inversely proportional to the concentration of the hydroxide ions. So neutral solutions will have equal amounts of both the hydronium ions and the hydroxide ions. And again, that concentration is equal to 1 times 10 to the negative 7th. And that's in moles per liter. So remember, brackets always indicates concentration in molarity. Now, what if we have an acidic solution? If we have an acidic solution, that means that we're going to have a larger concentration of the hydronium ions, and we're going to have a smaller concentration of the hydroxide ions. And remember that even in acidic solutions, we will still have some hydroxide ions present just due to the fact that water is present. However, the hydronium ions will be present to a much greater extent. So in an acidic solution, the concentration of the hydronium ions will be greater than 1 times 10 to the negative 7th, and the concentration of hydroxide ions will be less than 1 times 10 to the negative 7th. And again, those concentrations are in moles per liter. Now, what if we have a basic solution? Then the opposite is true. So we would have a larger concentration of hydroxide ions compared to the concentration of hydronium ions. So in that situation, the concentration of hydronium ions will be less than 1 times 10 to the negative 7th, and the concentration of hydroxide ions will be greater than 1 times 10 to the negative 7th moles per liter. So now, one way that we can measure acidity in a solution is by using something called pH. So pH is equal to the negative log of the concentration of hydronium ions. So let's say that we have just a pure sample of water. And we already saw that the concentration of water the concentration of hydronium ions in water is 1 times 10 to the negative 7th moles per liter. So if we calculate the pH using that concentration, we end up with a value of 7. Now, if you have a pH value exactly equal to 7, that means that your solution is neutral. However, if your pH value is less than 7, that means that the solution is acidic. If the pH of your solution is greater than 7, then it is basic. And again, if your pH is exactly equal to 7, then the solution is neutral. Now, in reality, if we measure the pH of a sample of water, it's not going to be exactly 7. There are other ions present in the water that we drink. So for instance, they add fluoride ions to water to help with the strength of our teeth. And then there are other minerals that just naturally appear in water. So sometimes water comes out to be slightly basic or slightly acidic, but it should be somewhere around a pH of 7. Now off to the right, there's a table of pH values for common substances. So your stomach, remember, contains hydrochloric acid. So human stomachs should be pretty acidic, and the pH should be around 1 to 3. Limes and lemons contain citric acid, so we would expect the pH to be less than 7 there, and we can see that it's pretty low. And then soft drinks also contain what's called phosphoric acid, and then also carbonic acid. So the pH is also less than 7 for soft drinks. And then if we go down a bit, we can see that our blood is actually a little bit basic. So the pH of our blood is around 7.4. And then if we look at household ammonia, which can be used as a cleaning product, the pH of that is around 10.5 to 11.5. And then last time we said that the NaOH is a strong base, so the pH of that would be really, really high, around 14. So what does the pH number imply? So this number tells us that the lower the pH value, the more acidic the solution. And then the higher the pH value, the more basic the solution. So because we're using a logarithm scale here, so remember pH is equal to the negative log of the concentration of hydronium ions, 1 pH unit corresponds to a factor of 10 in the concentration difference. So let's actually go back a slide. One thing that I didn't talk about on this slide was how to calculate the concentration of hydronium ions if you have a pH value. So down below at the very bottom, we can see that the concentration of hydronium ions is equal to 10 to the negative pH value. So we could always go back and figure out, for instance, in our stomachs, the pH is 1 to 3. So what is the concentration of those hydronium ions in our stomach? We could also figure out how many hydronium ions we have in human blood or in household ammonia. So for instance, if we have a concentration of hydronium ions that's equal to 1 times 10 to the negative 6th, the pH is equal to 6. And then if we have a concentration of hydronium ions equal to 1 times 10 to the negative 7th, the pH is equal to 7. So you'll notice that the pH value only increased by 1, but the concentration of the hydronium ions has increased by a factor of 10. So just keep in mind that, again, 1 pH unit corresponds to a factor of 10 difference in acidity. Now, the normal range for pH values is 0 to 14. So if we have a pH value of 0, that would correspond to a hydronium ion concentration equal to 1 mole per liter. And then if the pH is equal to 14, that means we have a hydroxide ion concentration equal to 1 mole per liter. So again, smaller values of pH correspond to very acidic solutions, so we can see that down below in this chart. And then really high values of pH correspond to a high concentration of hydroxide ions. And then of course in the middle we have our neutral solutions. Now, there is another way to express acidity or basicity of a solution, and that is pOH. So instead of using the concentration of hydroxide ions, hydronium ions, we can use the concentration of hydroxide ions to determine how acidic or basic a solution is. So pOH looks very similar to the calculation for pH, but this time we're taking the negative log of the concentration of hydroxide ions. And again, we can do the reverse calculation. So if we're given a pOH value, we can figure out what the concentration of hydroxide ions is by taking 10 and raising that to the negative of the pOH value. So that's just an inverse log there. So for example, in water, we know that the concentration of hydroxide ions is equal to 1 times 10 to the negative 7. So the pOH of water would be equal to the negative log of 1 times 10 to the negative 7th, which would just give us a value of 7 again. So neutral solutions will have a pH value of 7 and a pOH value of 7. But the difference comes in terms of basic and acidic solutions. So if you have a pOH value less than 7, your solution is basic. But remember, for pH less than 7, we say that the solution is acidic. So in the pOH scale, it's the opposite. And then if the pOH value is greater than 7, the solution is acidic. And remember that for pH, when that value is greater than 7, we say the solution is basic. So again, it's just the opposite. And as I said before, when your pOH value is equal to 7, then the solution is neutral. And down below, you can see the different scales. So the top scale is for pH and the bottom scale is for pOH. And you can see that they are directly opposite of each other here. Okay, so let's talk about the relationship between pH and pOH. So if we add together the pH and pOH for a particular solution, they will always add up to 14. So you can use pOH to find the pH of a solution or vice versa. So let's talk about why this is true. And I apologize if you can hear my dog in the background. He's a little bored today. Okay, so we have the concentration of hydronium ions, and if we multiply that by the concentration of hydroxide ions, we said that that was equal to the ion product of water, Kw, and that's equal to 1 times 10 to the negative 14th. So now, if we take the negative log of both sides, what we can do on the left is actually separate the concentration of hydronium ions from the concentration of hydroxide ions. So you might remember from some logarithm rules that if you're multiplying two things together inside of that log expression, you can actually add them together. So let's see what that looks like. So we're taking the negative log of the concentration of hydronium ions, and then we're adding the negative log of the concentration of the hydroxide ions. And then if we take the negative log of 1 times 10 to the negative 14th, we would find that that is equal to 14. And then earlier we said that the negative log of the concentration of the hydronium ions is equal to pH. And the negative log of the concentration of hydroxide ions is equal to POH. So everything connects together now. We started with our ion product constant of water, and we ended up showing that if you add together the pH of a solution and the POH of a solution, you always end up with a value of 14. So again, this is super useful because let's say you're running an experiment and you find, you find that the POH is equal to 6. You can very easily find the pH by taking 14 and subtracting the POH. So in this example, we would subtract 6 from 14, and we would get a value of 8. So the pH of the solution is 8, and sometimes it's easier to think about things in terms of pH. So in this case, we would say that the solution is basic. All right, so that's just a quick example of how we can use that. Now, one thing that's a little tricky with pH are significant figures. So the number of significant figures in the concentration of hydronium ions will determine the number of decimal places in the pH value. So for example, if we have a concentration equal to 1 times 10 to the negative 7th, we can see that we have 2 significant figures in our coefficient. And that's going to correspond to the number of decimal places in the pH value. So that's just one of those tricky rules that we have to remember for pH. And this also applies to POH as well. Now, this will also be true if we go in the opposite direction. So if you're given a pH value of 7.00, that means that your concentration value should also have 2 significant figures. Okay, so let's use everything we've learned so far to complete the following table. And we're going to assume that all solutions are at 25 degrees Celsius. This is number 52 in your textbook. So if you want to do some similar problems, there should be a few kind of around that problem. But let's start with the first row, and we'll do that one together, just as an example. Okay, so in the first row, we're given the concentration of hydronium ions. And then we need to determine the concentration of hydroxide ions, and then the pH, and then we need to determine if the solution is acidic or basic. Now, you could just right off the bat figure out whether the solution is acidic or basic based on the concentration of hydronium ions. So remember that if the concentration of hydronium ions is equal to 1 times 10 to the negative 7th, then everything is neutral. And then if the concentration, let me erase this real quick. So if the concentration is less than 1 times 10 to the negative 7th, then that means we don't have very many hydronium ions compared to hydroxide ions. So this would be a basic solution. And then if the concentration of hydronium ions is greater than 7, or 1 times 10 to the negative 7th, then that means we have a lot of hydronium ions, so this solution is acidic. So if we look at that concentration, we can see that that is a larger number than 1 times 10 to the negative 7th. So 3.5 times 10 to the negative 3rd is greater than 1 times 10 to the negative 7th. So we can already tell from that value that this solution is acidic. But if that isn't quite as obvious, you could also go through the process of determining the pH value. So let's do that. Let's figure out what the pH is. Okay, so we said that pH is equal to the negative log of the concentration of hydronium ions. So all we have to do here is just plug in that concentration that we're given. And if you want to pause the video and calculate this really quickly, you can. So the pH value that I got was 2.46. And again, we had two significant figures in the concentration value. So that means we need 2 decimal places in the pH value. Okay, so now the last thing we need to do is determine the concentration of hydroxide ions. So probably the easiest way to do this, is to use that ion product constant. So we were told that if we multiply the concentrations of each type of ion together, that it should always equal 1 times 10 to the negative 14th. So what we can do is rearrange this equation to solve for the concentration of hydroxide ions. So that would be equal to 1 times 10 to the negative 14th over the concentration of hydronium ions. So then all we have to do is plug in that concentration that we were given. And solve for the concentration of hydroxide ions. So if you want to pause and solve that, free. The value that I got was 2.9 times 10 to the negative 12th. So I'll just add that here to the table. Okay, so I would like you to go ahead and solve for the other rows in this table and pause the video if you don't want to see the answers just yet. And then when you restart, we'll go over those answers together. Okay, so let's solve for these other rows in this table. I'm going to use a different color for the second row. So for the second row, we need to solve for the concentration of hydronium ions in solution. So again, we're just going to use that ion product constant equation. And if we want to solve for the concentration of hydronium ions, we're just going to divide 1 times 10 to the negative 14th by the concentration of hydroxide ions. So once we plug this into our calculator, we should get a value of 2.6 times 10 to the negative 8th. And now we have the concentration of hydronium ions, so we can calculate the pH. And the value that we should get is 7.59. So this solution is slightly basic. So I'm actually going to write that in. And actually, in reality, I would consider this solution pretty neutral, at least in comparison to other solutions. Okay. So now for row 3, I'll use green. And this is going to be very similar to the first row. We can use the concentration of hydronium ions to figure out the pH. And we should get a value of 8.74. Oh, it's a little hard to see. Okay, and then we're just going to use that other equation, the ion product constant of water, to determine the concentration of hydroxide ions. I'm going to skip writing out that full equation. I'm just going to plug in the values. And we should get a concentration of 5.6 times 10 to the negative 6th. So looking at the pH, we can see that it is greater than 7, so we would consider this solution basic. And now for the last row. This one is a little bit different because we are given the pH, and we have to figure out the concentration of the hydronium ions and the concentration of the hydroxide ions. Now, there are a few different ways that we can figure this out. So, for instance, we could figure out what the pOH value is from the equation we derived earlier. Oh, meant to write 14 there. And then once we have the pOH, we can use this expression to figure out the concentration of hydroxide ions. And we also do have the pH value, so we can use this expression to find the concentration of hydronium ions. Or maybe we just figure out the concentration of hydronium ions from the pH, and then we use the ion product constant to figure out the concentration of hydroxide ions. So whichever method you choose to use is fine. I'm going to use the first method I mentioned, so I'm going to figure out the pOH, and then we're going to solve from there. Okay, so we're told that the pH is 7.15. Okay, so we're just going to subtract 7.15 from 14. So we should get 6.85 for the pOH. Okay, So now we can plug both the pH value in for the concentration of the hydronium ions, and then we can plug the pOH value in for the concentration of the hydroxide ions. So when we plug those values in, we should get a concentration of 7.1 times 10 to the negative 8th for the hydronium ions. And then we should get a value of 1.4 times 10 to the negative 7th for the hydroxide ion concentration. Now, from the pH, we can see that this is a fairly neutral solution. The pH value is pretty close to 7. Okay, so I hope that helps with understanding pH and pOH, as well as how to calculate the concentrations of hydronium ions as well as hydroxide ions. Now, we are going to talk about one more thing today, and that is pK. So pK is a way of expressing the strength of an acid or base. Now, last time we talked about acid ionization constants, or Ka. And that this was pretty similar to an equilibrium constant. Now, Kb is the same, but it's for bases. So it would be the base ionization constant. And Kb would just be equal to the products in a base reaction over the initial concentration of the base. Now, if we want to simplify the values that we receive for acids and bases, we can just use the pKa or the pKb values. So pKa is equal to the negative log of the acid ionization constant, and pKb is equal to the negative log of the base ionization constant. So this is kind of similar to our calculations of pH and pOH, but this time we're considering these ionization constants instead. You can also determine a Ka value or Kb value from the pKa and pKb. You just take the inverse log expression again, very similar to the calculations we did before. But this time, again, we're considering the ionization constants. Now, what do these values actually mean? Now, if you have a strong acid, the value of pKa will be really small. Now, keep in mind that Ka and pKa are almost inversely related to each other. So if you have a really large Ka value, so that means you have a strong acid, once you plug that into the expression above to calculate pKa, you're going to get a really small value because you are taking the negative log of that large value. So if you have a large Ka value, which means you have a strong acid, that means the pKa value will be really small. And it's the same for bases. If you have a really strong base, then that means you're going to have a small pKb value. And the same thing applies here as well, where if you have a larger Kb value, which means you have a strong base, then you're going to have a small pKb value because you're taking the negative log of the Kb value. Now, most often we're going to be dealing with Ka values, but it is good to be aware of these Kb values. They do come up occasionally. So last time we saw this table from your textbook, table 16.5, and this listed some acid ionization constants for monoprotic weak acids. And I did not include this last column last time. So the table was kind of cut off along the Ka column here. But this table does list these pKa values. And you can see that they're more compact values. They're kind of easier to see and use. So remember from the last slide that if we have a stronger acid, that means that we're going to have a smaller pKa value. Now, all of these acids are weak, but relative to each other, we can talk about strength. So in this particular chart, chlorous acid is the strongest acid, and phenol at the bottom is our weakest acid. And you'll notice that the strongest acid in this list, so again, this isn't actually a strong acid, it's just the strongest one listed. This has the smallest pKa value. And again, that's just for this list. And then at the bottom, we have the weakest acid in this list. And it has the largest pKa value in this list. So again, the smaller the pKa value or pKb value, that's going to indicate a stronger acid or stronger base. And then the larger your pKa or pKb value, that's going to indicate a weaker acid or weaker base. Okay, and that's all we're going to cover today. We are going to use these different types of values in the future, so it might seem a little bit random that we're talking about this right now, but we will use these in future calculations. All right, I will see you in the next video.